Today we're going to finish up section 1.5, which has to do with the curl of two vectors in R3. And we're going to start section 2.1, which has to do with systems of linear equations. The learning objectives are up there. And we will do, so first you'll be able to compute the area of an arbitrary parallelogram in R3 and the volume of a parallelepiped in R3. That's going to use the curl of two vectors. And separately, you'll be able to find the coefficients and constant terms in a system of linear equations, and you will understand what it means to be the solution of a system of linear equations. So, are there questions from last week? Okay. One question that several people asked after lecture was, does it matter how I compute the curl of two vectors? So everybody went to a different high school. Everybody learned in high school some trick to computing the curl of two vectors. I don't care how you compute it. I just want you to get the right answer without looking at someone else's paper. So whatever method you learned in high school is perfectly fine as long as it gives the right answer. So I do it one way, you do it another way. It doesn't really matter as long as you get the right answer. And part of getting the right answer involves that your method and my method all behave reasonably. And what we mean by reasonably is that no matter what vectors you use, the following are true. So for any vector x, any vector y, and any vector z in R3, and any scalar t, we have the following properties. First of all, if I compute the curl of x and y, and then I compute the curl of y and x, how should these be related to each other? Sorry, what? You just flip the direction. It's the negative. Secondly, if you compute the curl of a vector with itself, what should you get? Zero. The zero vector. Good. Third, curl plays well with vector addition. So if you add the vectors y and z, and then compute the curl with x, and you compare it to computing the curl of x with y, and the curl of x with z. Curl plays nice with addition. And finally, scalar multiplication plays fine with curl. So if you take x and then you multiply it by a scalar and then compute the curl, it's the same thing as if you just compute the curl of x and y and then multiply by the scalar. And it's the same thing as if you compute y, if you multiply y by the scalar and then compute the curl. All of these things follow directly from the definition. And if you asked me to construct some object that went from two vectors, that given two vectors gave me a vector that satisfied these, I would end up constructing the curl. All right, so what are some uses of the curl? So first of all, you know that it's useful in terms of finding planes and lines and that type of thing. So let's just quickly do two examples there. So exercise, determine the scalar equation of the plane that contains the points. I feel like I already did this one. No, I didn't. So they give us 3 points. The first point is the point P. It has Cartesian points -5, -1, 2. The second point is the point Q. It has Cartesian coordinates -1, 3, 4. And the third point is the point R. It has Cartesian points 3, 1, 1. And they're asking us to find something of the form n1 x1 plus n2 x2 plus n3 x3 equals d, or b, whatever they call it. Can't remember what they call it. All right. So you know that when you were talking about lines in the plane, you needed a slope and a point that the line went through. When you're talking about planes in R3, or when you're talking about planes in R3, you need a normal vector. So that would be n1, n2, n3, and a point the plane goes through. So that's what you need to write down what they're asking you for. So which is going to be the harder part, finding the normal or finding a point that the plane goes through? Finding the normal. You've been given 3 different points that the plane goes through. And so this is easy. So what you need to do is you need to find the normal. Now, you've been given that the plane contains 3 points. So you really, really hope that these 3 points are not on the same line. You really hope these 3 points are not collinear. Because if they were like this, then there are going to be infinitely many planes. Infinitely many planes that contain those 3 points, because all you have to do is make sure that the plane contains the line that the 3 points are on. So you're hoping that you've got 3 points that are not collinear. So you're hoping that that's a picture of P, Q, and R. How can you figure out if the points are collinear? So if they were scalar multiples of one another, then they would be collinear. And we can see they aren't. Good. So we know that we have hope. They're not scalar multiples of each other, because you just do it in your head. They're not scalar multiples. They're not collinear. So then what we need is we need to find 2 vectors that are parallel to the plane, or we need to find 2 directed line segments which lie in the plane. So remember, a vector starts at the origin and goes to a point. A directed line segment is a translate of a vector. It keeps the same direction, but its head and tail could be at different locations. So they've given us points, so we could compute directed line segments if we want. So how would we compute 2 directed line segments that lie in the plane? Subtract them. Okay, so let's pretend this is P and that's Q and that's capital R. This is all pretend. I mean, those are real coordinates, so I really could figure out which are which. So PQ, the directed line segment from the point P to Q, and the directed line segment from P to R, these are going to be in the plane. If I were to try and find the vectors that are parallel to them, that would be the vector Q minus the vector P, which is minus 1, 3, 4. Sorry. Minus 5, minus 1, 2. And this is going to be parallel to the line and have the same length as the line R minus P, which is the vector 3, 1, 1, minus the vector 5, minus 1, 2. So here, minus 1 minus 5 is minus 6. 3, 4, thank you. 2, good. Negative 2, 2, minus 1. Okay. So here I'm trying to be careful. This is the position vector for the point Q. This is the position vector for the point P. This is the vector that goes from the origin to the point Q. This is the vector that goes from the origin to the point P. And this is a vector which goes from the origin to some point. -6, 4, 2 is the same length and has the same direction as the directed line segment PQ. And similarly, this has the same length and it has the same direction as the directed line segment PR. So I want to find some vector which is orthogonal to P and Q, and it's orthogonal to the directed line segment PR. So I would like to take the cross product of these two. So you need to convince yourself that it's the same as finding a vector n, which is orthogonal to -6, 4, 2, and orthogonal to the vector -2, 2, 1, -1. So this is the geometric. See, the problem with all of these things is that you can have this beautiful geometric image, which has to do with real points and real directed line segments and real planes, and you've got all this geometry going on in your head, which is fantastic. And then next thing you know, there are these like vectors and cross products, and you need to be careful that you don't lose the connection between the geometry, which is this stuff, and the algebra, which is this stuff, and vector language. So in any case, this clearly tells you that if you take n to be the cross product, -6, 4, 2, cross -2, 2, 1, then you're going to be OK, because the cross product is orthogonal. And so that cross product is 4 minus 4 is 0, -4 plus 6 is 2, and -12 plus 8 is -4. Now let's see if I've made any mistakes.
It's -1.
OK, hold. The third entry's wrong?
No, it's -2, 2, and -1.
Ah, OK. 4
I think you did it right.
minus 2 is 4. Oh. I keep dropping negative signs, which I was thinking about it on Friday as just proof that I'm such a positive-minded person that I just can't bear negativity in my life. That's my excuse, and I'm sticking to it. All right, so -4 minus 4 is -8. Thank you. OK, well, -8, let's just take it. -8.
-10 and 4.
-10 and 4.
Yeah.
Now let's check that this is correct. So 6 times 8 is 56. Minus 40 gives us 16. Wait a minute. -6 is -4 is 48. 48 minus 40 is 8. And then we have plus 8 is 0. This dot product is 16 minus 20 is -4 plus, and then 16 minus 20. I don't believe this. -4? OK, let's do this again. 48 minus 40 minus 8. Yes. 16 minus 20 plus 4 is 0. OK? So we have our normal. Our normal is -8, -10, -4. Let me ask a question. Since I'm a positive-minded person, would it be OK if I chose a different normal, which is, let's say, 4, 5, 2? Yes. So all I did was I multiplied this by -1, and I divided out the common factor of 2. This normal will also be perfectly fine. It'll lead to a scalar equation which has different coefficients and a different b, but you will still be okay. So now that you have this normal, and you have 3 points in the plane, you can grunge through it and you can get your answer. One answer is -8x1 minus 10x2 minus 4x3 is -38. So the hard part was finding the normal. Okay. Now, geometry. Okay. So you recall that from the dot that if you have two vectors, the vector u and the vector v, or if you have the vector u and the vector v, then between these two vectors there will be an angle. So this is the angle theta, that's the angle between u and v. This is the angle theta, it's the angle between u and v. And we know that the dot product is nice. U dot v is equal to the magnitude of u times the magnitude of v times cosine theta. So this we know, and we got that from the law of cosines. If you sit down and you compute the length of u cross v, so you know what u cross v is in terms of u1, u2, u3, v1, v2, v3. You know what this is in terms of the components of u and v. It's some stupid vector, and you can compute its length. So you just take the square root, you square the first component, add the square of the second component, add the square of the third component. And if you grunge through this, then at the end of the day, you're going to get the length of u times the length of v times sine theta. So basically, you take the definition, that's a vector, you compute the length of that vector, you grind and you grind and you grind and you grind. At some point, you're going to use this. You grind a little bit further, and you're going to get to this. Now, in the book, the way they do this in the book is they actually compute u cross v. They compute the square of the length, and they find that it's equal to the square of the length of u times the square of the length of v times sine of theta squared. This is what they do in the book. So can anybody tell me why the book would have done things in terms of squares instead of just lengths? Because if you take the square, so squares, if you do it this way, you never see a square root, right? You just do this, and you're doing blah, 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 and you don't have any square roots. Then you get to this far, and you're like, okay, well, I didn't care about the square of the length. I cared about the length. So then you're like, well, let's just take the square root of this. So I take the square root on the left side, and I get u cross v. I take the square root on the right side, and I get the length of u, the length of v. And what is the square root of a square? Careful. You would like to say that the square root of something, the square root of a square is just a number, right? But what if I asked you about the square root of -2 squared? Is that just the number? No, we have to be careful. It's the absolute value. So this really is the absolute value of sine theta. Do I have to worry about sine theta being negative? No. This is where the book is very like it went to law school. It talks about the angle between the two vectors u and v. It doesn't talk about the angle from u to v. It talks about the angle between the two vectors. So if this is u and that is v, this is theta. If this is u and that is v, this is the angle between u and v. It is not that. If it were that angle, sine theta could be negative. So the book is very tricky in that it's very careful and it's very correct, but you need to be aware that when they say the angle between u and v, they're not talking about the angle from u to v, they're talking about the angle between u and v. And that angle is always going to give you a positive or 0 sign, because that angle will always be between 0 and pi. So this is correct, and you can use it. So this is a good, these two are good and useful things to know, and so now we're going to use them. Okay, so someone walks in off the street and they give you a parallelogram. And for $5, they want to know the area. So we're going to use the cross product. But the question is, why? I mean, why? Because it works. But what we need is we've been given a parallelogram. It has this angle theta. And you know for sure that A is equal to base times height. And so the height is, we drop down. We've got a right angle. So this, the base is the length of what? V. Using our friend from trig, the height is the length of u times what? Sine theta. And look, that is u times v times sine theta, and that is the length of u cross v. So if somebody gives you a parallelogram, all you need to do is know the vector for one side, the vector for the other side, and you compute the cross product. Okay, now let's be a little bit more serious. What if they had given you the vector, this is the vector 1, 1, and this is the vector minus 2, 2. So first of all, what is this angle? 90 degrees, or pi over 2. This is, in fact, a rectangle. And we know from elementary school that the area of this rectangle is, okay, so it's this times that length. So what's this length? Root 2. What's that length? Square root, what's root 8? So you take this and you square it, you get 4. You add the square of this, you get another 4. So you get the square root of 4 plus 4, which is the square root of 8. And so that's the square root of 16, which is 4. So we know this to be true. On the other hand, we can't take cross products of vectors in R2. Cross products are only for vectors in R3. So really, what you would do is you would take this and you would embed it in R3. So what would I take to be my vector u? 1, 1, 0. My vector v? Negative 2, 2, 0. And u cross v is going to be, let's see, this times that minus this times that, 0. This times that minus this times that is 0. This times that minus this times that is what? What's the third component? 4. And what's the length of that puppy? 4. Okay, so cross products give us areas of parallelograms. Okay, let's keep going. Now, what if you're given a parallelepiped? So after you figured out how to spell parallelepiped, you draw I did a good one in my notes. You have been given a vector u. You've been given a vector v. That is going to give you a parallelogram in a plane, in the plane spanned by u and v. You've been given some vector w, and w is the third side of the parallelepiped. And if we connected these dots and if we could draw, we would get a parallelepiped. Okay, that is our parallelepiped. Parallelepiped, and it has sides given by u, v, and w. So if it was on a test, you would be given a parallelepiped with vertices p, q, and r. That would give you p, q, and r. And then you would be given one more s. And you would be told that s is whatever, above that point or something. Given 4 points, you can get a parallelepiped. Okay, so we want the volume of the parallelepiped. So that's going to be, okay, so this is tricky. Now, if I have a deck of cards, I've got 52 cards. You know what the area is of each card. And when they're stacked up nicely, fresh out of the box, you've got the height. It's really 52 times the height of each card. You've got the height. So when you've got a nice rectangle, it's easy to compute the volume. You just say, well, it's the area of the base times the height. I've just taken it out of the box. Now, if I take those 52 cards and I shear them so that instead of nicely being stacked, it's slopey, have I added or subtracted any mass? No. All I did with that shear conserves as a volume preserving deformation. All I did was I took my nice, I guess it's not a cube. It's got 40 degrees, 90 degrees all around. It's a nice rectangular brick-shaped object. It's dead easy to compute its area. You've got the area of the base. You've got the height. So here, I've got the parallelogram on the base. I know how to compute its area. The area of the base and I need this height. So I need to drop w down to that plane. So I have the area of the base times the height. The area of the base we know how to get. So that's just the length of u cross v. What we need is the height. So we know how to get all sorts of things with, one way would be, well, you've got this point, find the shortest distance. You have this vector w. You would like to project that w onto what? The normal. So that's the big idea. So with that, you have your idea. I have w. I want the height. So idea, project W onto a normal. There are infinitely many normals. A normal vector and compute the length of the resulting vector. So that's the idea, and without that idea, you're stuck. So from this, we have that the height is equal to the length of the projection onto a normal vector of W. It doesn't matter which normal vector I take. So let me just write this out. This is the length of W dot n divided by n dot n times the normal vector. That is equal to, this is just some stupid number. I can take it out as long as I do an absolute value. So absolute value of W dot n over absolute value of n dot n. I don't really need that absolute value because n dot n is actually positive, times the length of the vector n. Can I simplify this any further? The denominator n dot n, how is it related to the length of the vector n? N squared. So if I really feel like it, I can simplify it one step further, because this is the length of n squared, that's the length of n. So I've got this far. And so now I've got the volume of my parallelepiped. Here we go. The area of the base is u cross v. And then I multiply it by the height, which is W dot n over the length of a normal vector n. That's super. So n is a vector normal or orthogonal to u and v. So that's great. Now, do I just stop here, or could I be even smarter? How could I be smarter? Yes?
Isn't u cross v equal to v negative of 9?
So that's the question. In principle, n is any vector orthogonal to both u and v. Right? There are infinitely many vectors orthogonal to both u and v. But what you're suggesting is, why don't I be smart about it? If I were asked for a vector which was orthogonal to both u and v, I would compute the cross product. So why don't I be smart and take n to be u cross v? There are infinitely many vectors that are orthogonal to both of them. That's a specific one. If I make that choice, then I get that the volume is equal to the length of u cross v times the absolute value of W dot producted with u cross v divided by the length of u cross v. Here I chose that specific normal vector. Those things cancel, and I get the absolute value of W u cross v. W dot u cross v, absolute value. So one thing that's nice about this, if I didn't actually know what my parallelepiped looked like, and if I didn't know for sure that this was u and that was v, if I was just given 3 vectors, I don't need to actually figure out this is u and that is v and that is w and put them in the right order. Because if I didn't know the geometry and I thought this was u and that was v, if I put u and v in the wrong order, this would introduce a negative sign, but the absolute value is going to knock out the negative sign. So this is just some formula you can blindly use without knowing which of the legs at the base is u or which of the legs is v. Now, really, you would like to know whether this is the same thing as u dot v cross w, because a parallelepiped is a geometric object. It doesn't matter which face you declare to be the base and which leg you declare to be the up. So this is something you would want to check in the privacy of your own home. Are there questions? So, yes?
So when you said up there you project W onto V, W onto a normal vector.
Yep.
Can you show on that sketch there what you mean by that?
So here is a normal vector. For sure, this normal vector is not u cross v because it's not long enough, but it's normal. When I project this vector onto that normal, I'm going to get this thing, which if I were to translate it over, would give me this. So it's the thing we did earlier with finding the distance between a point and a plane. Are there questions? Yes?
For that u cross v, can we use the formula design, or do we have to use the vector?
Well, the thing is that if you wanted to use length u, length v, sine theta, the problem is that you'd have to actually figure out what is sine theta. And short of drawing the things and measuring the angles, you wouldn't be able to find sine theta. And so you'd be like, oh my God, how do I find sine theta? And then some person would say, well, just use the cross product. And that's ultimately what went in here. Are there questions? Okay, so I'm not doing any examples because the examples are all in the book. And it's easy for these types of problems to just do examples and not think about the geometry and just memorize formulas. And then it's all sort of, for me, an empty exercise because I don't like memorization. If you're good at memorization, memorize the formulas and learn how to use them. And you don't have to worry about the why. And that will, no doubt, carry you to at least a B in the course. Okay, so we're moving into a new chapter, which is the solutions of systems of linear equations. And I want to start with an example so that you'll see where we're going. So here we have two linear equations, and I'm just doing two equations and two unknowns because it allows me to draw. So the first equation is x1 plus x2 equals 2. The second equation is 2x1 minus x2 equals 7. The unknowns, or the variables, are x1 and x2. The coefficients are 1, 1, 2, minus 1. The right-hand side, or the constant, is 2 and 7. These are linear equations because we don't have anything like x1 squared equals 2. That would be nonlinear, where the unknown shows up in a nonlinear manner. These are linear because the unknowns are standing alone. They're not inside of functions. Okay, so I am seeking a solution of these two equations. So I go back to middle school, and I draw two lines, x1, x2. The first line is this one. So these are the points that satisfy x1 plus x2 equals 2. That's the point 0, 2. That's the point 2, 0. There are infinitely many points which satisfy this one equation. Now I can draw all of the points which satisfy that equation. Two x1 minus x2 equals 7. This is the point minus 7, 0. This is the point 7 halves, 0. So every point on this line satisfies the first equation. Every point on this line satisfies the second equation. We are seeking all points which satisfy both equations. So that would be this point right here, and that is going to turn out to be the point 3 minus 1. Agreed? Now, what we're going to be doing tomorrow is doing an algorithm which allows us to find this point. And what it does is it goes from a linear system that's hard to solve to a linear system that's easier to solve, to a linear system that's easier to solve, to a linear system that's so easy to solve, it's embarrassing. And so the idea is that we change linear systems. And as we change linear systems, these things can change. The thing that cannot change is that point. So let's do this, and we're going to do it not in the way you would have done it in high school, because if you were in high school, you would have been like, ooh, here's a plus 1, here's a minus 1, let's add them together, solve for x1, then solve for x2. That method works perfectly fine for this particular pair of equations, but it required your brain, right? It required you to look and say, ooh, these coefficients are going to work out nicely, and I only have 2 unknowns, and so if I just add these 2 together, I can solve for x1, and then done. And your brain is a wonderful, beautiful thing, but it's not inside of a computer program. And ultimately, we want a crank that can be turned so that if someone walks in off the street and gives you 45 equations and 47 unknowns, you can actually turn the crank and find whether or not there is a solution, and if there is a solution, what the solution is. So I'm going to just start turning a crank. I'm not going to do the smart thing, which is to recognize that. So please don't ask me why I didn't do the smart thing, because I'm trying to generalize. So the first step is to replace equation 2 with equation 2 minus 2 times equation 1. So I'm keeping equation 1, x1 plus x2 equals 2. Now I replace equation 2 with equation 2 minus 2 times equation 1. So I have 2x1 minus 2x1. I have minus x2 minus 2 times x2. So that's minus 3x2. On the right-hand side, I have 7 minus 2 times 2. That's 7 minus 4 is 3. OK, so at this point, I'm going to do the exact same high school thing. I have the first line, which is unchanged. These are all of the points that satisfy this. The second line is this. So that is all solutions of 3x2 equals 3. And this is still the point 3 minus 1. I have changed the lines. I have not changed the solution. Now, I'm going to continue cranking, because this is, you're going to see it's a crank. Step 2 is replace equation 2 with minus a third of equation 2. So x1 plus x2 equals 2. I replace this with minus a third of that equation. So that gives me 0x1 plus x2 equals what? Minus 1. Here's the picture from high school. This is all points that satisfy x2 equals minus 1. Are these lines the same? No. Yes. Because if you have an equation and you multiply it by anything other than 0, you haven't changed the solutions of the equation. Step 3. Replace equation 1 with equation 1 minus equation 2. Oops. So I'm going to be replacing equation 1, so I'm going to go ahead and copy down equation 2 while it's still in my memory. So equation 1 minus equation 2. This minus this is x1. This minus this is 0. This minus this is 3. Now, I plot all points that satisfy the first equation. That is x1 equals 3. I plot all points that satisfy the second equation. That is x2 equals minus 1. And here is the point 3 minus 1. OK, so what was the point? I started with a system. I followed an algorithm. And I ended up with a new system which had the same solutions as the old system. But this one, it's just staring you in the face. If I gave you this system and I said, please find all solutions of this linear system, please find all solutions of this linear system. Right? Now, you could say, and you can say correctly, that you could have really stopped here. Because at this point, you could solve for x2. You get the x2 is minus 1. And then you back substitute, and you find the x1 is equal to 3. So you could do this and stop and do back substitution. But what we're going to do in tomorrow's lecture is do this carefully and convince you that we can do these things without messing up the solutions.